Hi guys, these are your notes for Atwood machines and modified Atwood machines. So this is a modified Atwood machine. You have one mass hanging, the string goes over a pulley, it hangs onto or is attached to, the other mass. It's sitting on a table or on an inclined plane or something. This is a true Atwood machine. So you just have two masses hanging from the same rope over a pulley. We'll get to this one at the end. I think it's a little bit easier to start with modified Atwood machines. So we're gonna start with them. So we make a couple of assumptions. We're always gonna assume that our ropes are massless and our pulleys are frictionless when we're studying forces. So if they give you a question where they're like, so here's your thing, calculate what the acceleration should be, and you calculate the acceleration, and then they say, oh, but the acceleration was only this much instead. What happened? Well, your pulley had friction in it. So the pulleys being frictionless is kind of like the thing that we assume. If something goes wrong, it means that your pulley was not frictionless. Sometimes I've seen it done where they give you a pulley with friction and then ask you to calculate the torque that's on it. And we're going to go over that one a little bit more when we get to rotational motion later. But for now, for this, we're taking it easy. Our pulleys are frictionless, ropes are massless, everything is super easy. So if a force pulls on one end of a rope, the tension in the rope equals the magnitude of that force. So if you are just pulling something, so if this part doesn't exist, if you're just exerting a force over here, pulling on this rope with this mass attached to it, that force that you're pulling with is exerted at all points in the rope, just because it's easy. Is that exactly true? Heck no. Our ropes have mass, our force is dispersed, blah, 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 but take the easy way, guys. If those two objects are connected by a rope, the tension is the same at all points in the rope. So that's saying that the tension here is going to be the same as the tension up here. And if that rope passes over a pulley, the tension in the rope is unaffected. So this isn't exactly true. Again, there's friction in your pulley that exerts a torque and blah, 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 blah. But for now, tension is constant at all points in this rope. So the mass of this block on the table is 42 kilograms and the mass of the hanging block is 18 kilograms. And they tell you that the table is frictionless, which helps us out considerably. I'm just going to label these. So we're going to start by drawing a free body diagram for each object because it is a forces problem. So we're going to start with our forces stuff. So this is for block 2, the block on the table. I've got a pretty considerable force of weight pulling it down. It is on the table, so I've also got that normal force. Oop, I misjudged. Pretend those are the same length. Holding that block up on the table, not letting it fall through the table. And then I have some tension from that string pulling on this block. That's it. There's no friction. I don't have anything else to worry about. I just have these three forces on block 2. For block 1, the hanging block, I've got its weight pulling it down. Oh, I should have labeled that. Oh, and this one actually should be a little bit smaller than the other one. I mean, like half as long as the other one, but I'm just going to go with this one because I want to be able to see my picture. And then I've got tension pulling it upwards. And I'm not really sure how long to draw this force of tension here. I'm not sure if it's accelerating. I'm not sure if it's just hanging out. I'm pretty sure it's accelerating because I have no friction holding this back. I don't have any forces holding this system steady. I've got weight from this one pulling it down. I don't have anything up here holding it left. So, you know. So this is the tension on block 2. This is the tension on block 1. And like we're about to see, I should have drawn these to the same length. So I'm going to adjust that real quick. because it's easy to fix yourself. Yeah, that's better. Because those two are an action-reaction pair. I know the force of tension on block 2 is going to be the same as the force of tension on block 1. So I've got the tension in this rope that is resisting mass 1's fall towards the ground is going to be the same as the tension in this rope over here, pulling mass 2 towards the right. So my net external force on the system, this force is an internal force. Same with this one. If you look, my normal force of mass 2 is going to be equal to the weight of mass 2 because it's not inclined. I don't have anything weird going on vertically over here. These are going to be equal. I have no net force coming from either of these. The force that causes the acceleration of this entire system is going to be the weight from block 1. That is it. So my net force, my net external force on my system is going to be that force weight from block 1. That is the only force that is coming from outside my system that has any sort of impact on that system's motion, which sounds a little scary. So that's the weight of mass 1 is the mass times the acceleration due to gravity. So I've got 18 kilograms times 9.8 meters per second squared. And that is, I forgot, 176.4 newtons. So this entire system of this mass and all the strain and the turning of the pulley, all of that is being caused by this one external force. So to find the acceleration of the system, I have my net external force. It's just that one force. It's just that force of weight from block 1 pulling it down. And I know that that is equal to the total mass of the system times the acceleration of that entire system. And that's what we're looking for, so I'm going to rearrange. The acceleration of your whole system is equal to that force weight from block 1 divided by the total mass of the system. So it's 176.4 newtons, and I'm going to divide that by my total mass, so my 18 kilograms plus 42 kilograms. This is why I use pencil. So 176.4 divided by 18 plus 42, 2.94 meters per second squared. So that means that both of these blocks are going to accelerate at 2.94 meters per second squared. This one is accelerating downwards at 2.94. This one is accelerating to the right at 2.94 meters per second squared. They are connected by the same rope. They have to accelerate at the same rate. So now I want to find the tension in the rope. And what I have to do is the same thing that I did when I was going over those systems of objects. I just have to pick one of these blocks and redefine my system as only that block. And you can do it with either block 1 or block 2. Doesn't matter. Take your pick. Do what you think is easiest. I'm going to choose block 2. And the reason I'm going to choose block 2 is because block 2 only has one force in the direction of your acceleration. Remember, your acceleration for block 2 is to the right. Your acceleration for block 1 is down. I've got two forces acting in that direction, so parallel to that direction. I've got my tension resisting that acceleration. I've got weight causing that acceleration. So I've got two forces here. That's more to deal with than just this one force. Now, if I had friction, then it would be about the same. So I'm just going to do this one for now because, again, there's only that one force. I'm going to let my life be easy. So I know that the sum of the external forces on block 2, my block that's up on the table, is going to be equal to that tension. And I know that tension is the only force that causes that mass to accelerate. And we can put a subscript of 2 on the acceleration. It doesn't really matter because your acceleration for the entire system is going to be the same. So I know that tension is going to be equal to that mass of block 2, that 42 kilograms, times the acceleration of it, that 2.94 meters per second squared. So that tension is, nope, 123.48 newtons. Now, I'm also going to do this with block 1 because I feel like I probably should. Remember, we've got acceleration going downwards. I've got my tension resisting that acceleration, holding it up. I've got that weight going downwards. So what I'm going to do, if I do my sum of my forces on block 1, my weight is in the direction of acceleration, so I say that's positive. My tension acts in the opposite direction of acceleration, so that's negative. That's the sum of my forces. That's going to be equal to the mass of that object times its acceleration. Again, I'm looking for the tension, so I'm going to add this to both sides, and I'm going to subtract this one from both sides. So I'm basically just swapping these things places. I know the weight of block 1 is its mass times its gravity. So I've got that 18 kilograms times 9.8 meters per second squared minus its mass, that should be kilograms, sorry, times its acceleration, which is this one, 2.94 meters per second squared. And when I put all those numbers in, I get 123.48 newtons, which is excellent because that tension is equal to this tension. The tension at all points in that rope is the same. So this just shows you that it doesn't matter how you calculate that tension. Pick the easy way, pick the hard way. You should get the same number as long as you don't do a boo-boo in your math. So let's do one more modified Atwood's problem. This one, there is friction. So this one's a little bit more complicated. We've got a 20 kilogram mass on the table and a 38 kilogram mass hanging. And then they give me a coefficient of friction between the block and the table is 0.25. So again, I'm going to start with a free body diagram. Block 2 is my block on the table. I've got weight going down towards the center of the earth. Oops. I've got its normal force perpendicular to the surface. I've got that tension pulling it. And now I have friction resisting its motion. And I'm not sure about the magnitude of the force of friction compared to the force of tension. So I'm kind of just going to draw it about that length. We'll see if anything happens. And they don't even tell me that this is static or kinetic friction. So again, we're kind of just winging it. We're going to find out. For block 1, the block that is hanging, I've got its weight going down towards the surface. Oops. Yep, 1, sorry. And this one is larger than this one, so I drew it longer. And then I've got tension pulling it up or resisting its fall towards the ground. And again, the tension in the rope is the same, so this force is the same as this force. And I tried to draw them the same length. I think I got pretty close, but not exact. Let's be real, this one's longer, but I did my best, guys. And I'm just gonna call that tension. I'm just gonna let my life be easy on this one. So again, I wanna find the net external force on the system. So I'm just gonna do a good old-fashioned Newton's law. So I've got to find all of my external forces. I've got this one causing an acceleration. It's going to be in the direction of acceleration, so I say that's positive. And then if you look, you've got friction over here resisting the acceleration of this system. So friction is holding this block up on the table. It is resisting this block's fall towards the ground. So that friction is going to be negative. I didn't include the normal force and the weight because these don't cause any acceleration because these are perpendicular to the surface and there's only acceleration along the surface. So I'm going to calculate my force weight from block 1. It's going to be its mass times gravity. I'm going to have my force of friction from block 2, which is, oh sorry, I should have put a subscript on there. Its coefficient of friction times the normal force from block 2. I don't know what that is, but I do know that it has to be equal to my weight. Has to be equal to my weight because again, there is no incline, there's no angles. I got nothing saying that these two are not equal. So the mass from block 1 times gravity minus the coefficient of friction times the mass of block 2 times gravity, because my normal force is equal to the weight of block 2. Weight of block 2 is mass times gravity. So it's going to be my 38 kilograms from block 1 times 9.8 meters per second squared minus my coefficient of friction, 0.25, times the mass of block 2, 20 kilograms, times acceleration due to gravity, 9.8 meters per second squared. I'm going to slap all that into my handy dandy calculator. 38 times 9.8 minus 0.25 times 20 times 9.8. So then I find that my external force, the net external force that causes the acceleration of that system is going to be 323.4 newtons. Now I can hear some of you saying, Miss Meiber, shouldn't that be negative? Well, I am maybe, almost, kind of, sort of. Again, it depends on which direction you say is positive. I said that the direction of my acceleration is positive, so even though this is accelerating downwards, that's my positive direction here. And then this one's accelerating to the right, which is generally considered positive anyway. So things get kind of wonky with these systems. You have to remember that the right direction for this is the positive direction that is down for this one. So you just kind of gotta do your best and keep it straight, my angels. So I want to find the acceleration of that system. That acceleration is going to be equal to that net external force we calculated divided by the total mass of the system. This is just Newton's second law in a different, pretty way. So it's going to be that 323.4 newtons. I'm going to divide it by the sum of the mass of my system. So it's going to be 38 kilograms plus 20 kilograms. And divided by 5.58 meters per second squared, which is pretty fast. I mean, it's not like, oh my god, fast, like nothing we should worry about fast, but you know, that's a good speed. Good rate of acceleration, rather. So, good job. And then again, I want to find the tension in the rope. Again, there are two different ways to do it. We could use block 1, that tension and that force is equal to the mass of block 1 times its acceleration. We could do it with block 2. Ooh, sorry. So that tension and that friction. I'm going to do this one just because I like it. I'm going to skip doing it with both of them for this time because I trust in my ability to do math. Now, if you try it at home and you decide, or if you figure out that I'm wrong, please let me know so I can fix this video and pretend it never happened. I don't like to look dumb. So the sum of my forces for block 1, I've got that force weight of block 1 going in the direction of acceleration, so I say it's positive. And I've got that tension resisting its motion, so I say it's negative. It's going to be equal to the mass of block 1 times its acceleration. I'm looking for tension, so I'm going to switch that guy over there. That guy's going to come over here, so I'm going to end up with the weight of block 1 is its mass times its gravity. So it's that 38 kilograms times 9.8 meters per second squared minus its mass again times its acceleration. So you should get 160.36 newtons, which is perfectly reasonable because we've got a pretty heavy block hanging down over there. So there are easier ways to write this. You could have factored the mass out, like you could have done, this is mass times gravity minus mass times acceleration. You could have factored that out to be mass times gravity minus acceleration. That would have worked just fine. I didn't think it was worth it for this problem. It's just one more step of math to save us typing in 2 numbers. Didn't seem like a big deal, but we are going to do this for our next problem. So if you are uncomfortable with factoring things out, you should pretty please ask me for help. Remember, I like to help. I love you very much. I want to help you. So for this one, we've got a 100 kilogram set used in a play, stored in a loft above the stage. The rope holding the set passes up and over a pulley, then is tied. The director tells Carol, who has a mass of 50 kilograms, to lower the set. When she unties the rope, the set falls and Carol is hoisted into the loft. So we get to just pick which direction is, like which one of these is going to be Carol and which one is the set. And I'm going to say that this one is the set. And this one is Carol. And we get to pick that because that's the way that we picked it. Good job, us. So I want to draw a free body diagram for each object. For Carol, she's got 50 kilograms of weight, or 50 kilograms of mass, which is many more newtons of weight, excuse me, holding her down, and then she's got that tension pulling her up, and that tension acting on Carol is greater than her weight because they tell us that she is hoisted into the loft. So she's going to accelerate this way. Oops, sorry. And then for the set, it is going to have a larger weight. Pretend that's twice as long as Carol's. And that same amount of tension. And this set is going to accelerate downwards. So what is upwards for Carol is positive. What is downwards for the set is positive. I want to know what action-reaction pairs are present just because that helps so much. The tension of the set is going to be equal to the tension of Carol. And again, I'm just going to call it the tension. So what happens in an Atwood's machine, this one is going to move down, the other one is going to move up. They're going to accelerate at the same rate, just like they have been doing for our modified Atwood's machines. So for this side of my problem, positive acceleration is downwards. For this side of my problem, positive acceleration is upwards. I'm going to show you something. If you don't like it, you don't have to think of this ever again. You've got a pulley. Normally, you have the two strings hanging down to the sides. We're going to pretend we just lifted them. So this over here is going to be my 100 kilograms from my set. This over here is going to be my 50 kilograms from Carol. So as this 100 kilograms moves down, which is now to the right, this 50 kilograms is going to move up, which is now to the right. So some people like to think of it like this. Some people like to think of it like this. Again, do what's best for you. Do what makes your heart happy. So I'm going to do Newton's second law for each object to determine the acceleration of the system. So you can do this the way that we have been doing it, where you find the net external force on the system, and then you find the tension in it, and then you blah, blah, blah. That will work. This is just a different way of doing these problems. Do whichever one works best for you. So the sum of my forces on Carol, I have upwards the tension, downwards I have Carol's weight. That is going to be equal to the mass of Carol times the acceleration of the whole system. This one, the sum of my forces on the set, I could just leave it as S. In the positive direction, I have the force weight of the set. In the in the negative direction, I have already confused myself with positives and negatives. Sorry, guys. I have the tension acting opposite the direction, so I say it's negative. That's going to be equal to the mass of the set times the acceleration of that whole system. So what I'm going to do, I know that those tensions are equal to each other. I'm going to solve this for the tension. So tension for this one is going to be the mass of Carol times the acceleration of the system plus Carol's weight. The tension over here, I'm going to switch these, move these to opposite sides. I'm going to have the force weight of the system minus the mass of the set times the acceleration is going to be equal to the tension. Over here, mass of Carol times the acceleration plus the weight of Carol is just the mass of Carol times gravity. Over here, I've got the mass of the set times gravity minus the mass of the set times the acceleration. And these are going to be equal to each other. So I set these equal to each other. So I'm looking for the acceleration of the whole system. I'm going to bring all of my acceleration terms to one side. So I'm going to add this. It's being subtracted. I want to add it. I'm going to subtract this one. So I'm going to end with, well, not end. End is a strong word. Oh. Nope, doing good so far. I'm looking for the acceleration, so I'm going to take the acceleration term out. And then I'm going to do it again on this side, just because that's kind of what the convention says to do. I'm looking for the acceleration, so I divide both sides. I'll put parentheses in there so you guys feel a little bit more comfortable. So I'll find that the acceleration of my system is equal to the difference in the masses divided by the sum of the masses times gravity. And this is true for every Atwood's machine that does not have internal friction in the pulley. A lot of times what they do is they just write it as the acceleration of an Atwood's machine is equal to m1 minus m2 divided by m1 plus m2 times g. Either way, remember, it's just got to be the difference divided by the total multiplied by gravity. If you switch these up, if you put the plus on the top and the minus on the negative, that just means that you're going to have a value greater than the acceleration due to gravity. That can't happen. If you get that, you have done a dumb. Go back and fix it. I, again, am not sure that they're going to ask you guys a question like this. I apologize for taking the chance and skipping it the first time around, but at the time, it was a good risk to take, and I will stand by that. If you guys have any questions about this, please, please, please let me know. We can go over this in Blue Jeans during class if you'd like. I love you. I hope you guys are having a great day. Bye.